So let's discuss kinematic stacks when they involve both position, velocity, and acceleration. So let's suppose I've got a situation where, let's look at the velocity graph as a function of time. Velocity as a function of time. Now I'm not going to put units or numbers on it, and that's what I mean by qualitative. I just want to, describe in general terms what's going on with an object. And suppose an object at first is moving with constant velocity. And let's suppose that velocity is positive. So it's like your car is driving. And then all of a sudden you start to slow down. But then you keep going like this. So this one's even more complicated than the one that you're going to do in the homework for the next assignment. So what does this mean? This is positive velocity, this is negative velocity. So let's just think about it in terms of the velocity of the object. At first, what's the object doing? It's moving. What direction is it moving? It's moving in a positive direction. And then all of a sudden, what happens? We start slowing down at a constant rate. Slow down. What happens right here? Our velocity is what? So that means that we have stopped. But what happens in the next moment? Yeah, so this means that we're slowing, stopping, and then changing directions and moving in the opposite direction. Now this is kind of like if you throw a ball up in the air. It's going up and up and up and up, and then for an instant, right, it stops. But it doesn't stop and hang there, does it? I mean, only in Looney Tunes cartoons will they stop and hang there. It goes up and down, immediately starts going down. So that's what that means. So what we're going to do is, from the velocity versus time graph, we're going to draw an acceleration versus time graph. And we draw it directly below it. Now, whenever you see a change, I always draw a dashed line, kind of like this, because that's where the change happens. So what was my acceleration for the first period of time? Well, what's the slope of this line? My velocity is constant. There's no change in velocity, which means my acceleration is 0. So this is acceleration as a function of time. But then what happens? At this instant in time, what's happening to what's the slope of this guy? Yeah, it's negative. The velocity starts decreasing at a constant rate. And that's what acceleration is the rate at which we decrease or increase our velocity. And since here the slope of this is constant but negative, our acceleration is negative. So that's what the acceleration looks like. Because acceleration is the slope of velocity. Okay. Now, we also want to draw the position as a function of time graph. I'm just going to keep it all positive. But I could stand down. I mean, I could have a situation where I would have a negative position. Now, where do I start? If I'm given my velocity graph, I really have no idea where to start. And so on a test, if I gave you this on a test and ask you to draw this and this, what I'll do is I'll put a dot and say, that's where you're going to start. I'll tell you where to start. If I don't tell you, you can start wherever you want. Now, what's true about my velocity? It's constant and positive. So velocity is the slope of position. So here's my position graph. So this is saying, hey, the slope of your position graph is going to be positive but constant, which is a straight line, isn't it? Now, how steep do I make that? If it's a qualitative map or qualitative kinematic sec, doesn't matter. Just make sure it's a positive slope. But then what happens to my slope? What happens to the velocity? The velocity gets less and less and less and less and less until it's zero right here. Now, if I've got a place where the velocity is zero, I'd like to draw a dashed line like this. And that means, hey, my velocity is a little bit less, 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 until what happens right here? My slope is zero right there. But then what happens over here? The slope becomes, the velocity is negative, so the slope becomes negative, and it gets more and more and more and more negative as time goes by. So negative, 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 negative. So what this is a straight line, and this is like a parabola that's upside down. And we're done. And this is where it's a little bit more complicated. I think on the homework, than what's on the homework, we don't go beyond here. I think on the homework it's just going to kind of look like that. But this is how you draw a kinematic stack. I'm going to give you the velocity versus time graph. You'll have to figure out what the acceleration graph is and what the position graph is. Any questions? Yes?
Do you want the position versus time graph always above the velocity versus time graph?
So the question was, do I always want the position versus time graph on top of the velocity versus time graph? That's a good way to do it. Now, sometimes it might get a little mixed up, and you might find yourself putting the position on the bottom. It's okay. I'm not going to mark you wrong. I'm not going to take points off for it. But I would say you'd be better off if you do this, because there's a logical order here. Look, what if I gave you this graph? I could, by looking at the slope, I could get this graph. Oh, look, positive constant slope. Oh, constant velocity. Oh, look, the slope's getting less and less and less until it's zero. Velocity is getting less and less and less until it's zero. And now it keeps getting less, we have a negative slope. So if I gave you this, you could derive this. Derive, the derivative is the slope. This function describes the slope of this function. And then from this, I could derive this. Zero slope, zero acceleration. Oh, constant negative slope. Constant negative acceleration. Now, what if I gave you this? You could work your way up. Oh, zero acceleration, constant velocity. Now, that doesn't tell you what the constant velocity is, does it? So I would have to tell you. So if I gave you this graph, I'd have to put a little dot right there and say, okay, your starting velocity is right here. And then you would say, oh, if I start right here, constant, and then, oh, negative slope. And then you go up to the next one. So you can go from the bottom up or from the top down. Also, there's another thing. I've been talking about slopes here, but there's also areas. Look, what's the area for this part? Zero area under the graph. There's no change in velocity. Remember, we said that the area underneath an acceleration versus time graph represents change in velocity. Well, if there's no area, underneath the graph, right, the acceleration is 0, there's no change in velocity. But here, look, negative area, right? The area of this represents the negative change in velocity. And then we'll go here. What is the, so this area here represents the change in velocity. And I look right here. Oh, I got velocity. What does this represent here? Oh, that represents my change in position. What was my change in position? From starting from here, I went up to here. And then what is this? That's another change in velocity from here up to here. So this represents another change in velocity. And then what about this area right here? Oh, notice that that's a negative area, isn't it? This is negative because my change in position will be in a negative direction. We started here and we went down to here. So when you're looking at areas and going up the kinematic stack, that's called integration in calculus. If you start here and work your way down, that's called differentiation in calculus. If you're in AMA, you'll get to that at the end of the year. Okay? All right, that's enough. That is all.